All right, number 2, we are given that segment ED is congruent to segment EF. So I mark them, and I will say that with marking those, I did notice that I'm dealing with an isosceles triangle here, and we know that if two sides of a triangle are congruent, the angles opposite them are congruent. So this does, if I need it, it does tell me that angle 5 is congruent to angle 6. So I'm going to go ahead and mark it. EH is congruent to EG. Now this one is a little bit tougher to mark because of points J and K that are interrupting those segments. So I'm just going to make these both orange. So I know that the orange segments are the same, and if you really are a color person, we also know that these yellow segments are the same. My last given is that, more with the orange. The yellow gave me that. The orange segments are also part of an isosceles triangle, which do, if I needed it, lead me to the fact that those two angles are the same. And then I'm given that angle 1 is congruent to angle 2. So our task is to prove that triangle DJH, terrible DF, DJH, this little guy down here, is congruent to triangle FKG. The little guy down here. So right now, for the red and the green triangles, I have exactly nothing marked, which is a problem. I have no vertical angles. I have no reflexive property. I have nothing. I have no sum of the parts that could help me out. I have these angles that are outside of the triangle, but even still, they're not inside, and there's no way to get them inside. So we're kind of stuck. And sometimes when you're stuck, this is where I say, okay, would proving a different set of triangles first be helpful? And also considering what the heck was the purpose of these givens. Now, I will be honest with you, when I was first looking at this proof, I had some think time because I got hung up on the fact that I was going to be proving these purple triangles. And I was thinking, okay, I have ASA in both of those purple triangles, which I do. I can absolutely prove that those purple triangles are the same. But then I got stuck with, how does that help me with the red and green? And that's where I was totally at a loss. It helps me with the red and the green because I could steal that these match, and that gives me a side, but there's really nothing else I could steal. I know that these angles match, and I could do a lot of math to prove that the angles supplementary to them match, but I still only have 2 items for the green and the red, and that's not enough. I need 3 things, and so I was stuck. And then because I was stuck, I realized, okay, you're being closed-minded. Maybe it isn't those purple triangles. Maybe we should look at a different set. And there are more sets. And so I was thinking about, all right, what else is this yellow side and this orange side a side of? And I'm not sure why I didn't think to use the orange side completely, but if I go up the given side and down the other given side and then connect the dots, I do have a triangle. And if I do the same thing, this yellow was given, this orange was given, and connect the dots, and I have a triangle. And in fact, the angles up at the top, angle 1 and angle 2, those were given also. So those purple triangles are definitely congruent by side, angle, side. Okay, great, but does it help me? And this is a case where it does help me a little bit because it gives me some more information inside this triangle. It leads me to the fact, it gets me this side is congruent to this side by CPCTC. And it also gets me that this angle matches this angle by CPCTC. And it could lead me to the conclusion that this matches this by by CPCTC. However, I would then have to do sum of the parts and subtraction to prove that angle 3 and angle 4 are the same. So I could do it. It works. It's helpful. But sometimes I like to look at a question and say, hey, maybe could I avoid using sum of the parts? Is there any way to dodge that? And really, there are other ways to approach this question. But we either have to deal with sum of the parts, or potentially we'd have to deal with using something like if two angles are supplementary to the same angle or congruent angles, then they are congruent to help us get this angle here and this angle here. So we have options. I want you to go ahead and try this proof your way, but my solution is just going to be a sample solution. And please remember that there is absolutely more than one way to complete this question. All right, so your method may or may not be the same as my method. There really are tons of different ways to do this question. Someone could even use vertical angles in a way that makes this work. But instead of even touching the blue triangles, I'm only going to prove the purple triangles are congruent. So I am proving two sets. My first set is going to be that triangle EDH is congruent to triangle EFG. And I will be using side, angle, side. My first pair of sides, DE congruent to FE. Those were given. My angle is angle 1 congruent to angle 2, also given. And my third pair of sides is side EH congruent to side EG. And that was given. And because these are all givens, this is a relatively easy proof, so I'm going to press pause and go ahead and prove those triangles. All right, now I have to decide what am I going to steal from the purple that's going to help me to get the red and the green. I am going to steal sides DH congruent to GF. That gives me a side. I'm going to steal angle, I can't call them H and G because there are other angles there. So how many numbers do I have? 1, 2, 3, 4, 5, 6. I'm going to have to call these 7 and 8. So I have a side and an angle. And I do have to get another angle. And the other angle I'm going to get is these angles in here, 3 and 4. And then I'm working with angle, side, angle. So to prove the red congruent to the green, I'm going to use angle, side, angle. My first pair of angles being angle 7 congruent to angle 8. That is just direct CPCTC, stealing them right from the purples. Then I'm going to get side DH congruent to side FG. It's totally not legible, sorry about that. That too is straight CPCTC. So those two pieces aren't bad, but then angle 3 and angle 4, those are not angles in the purple. The purple angle is a little bit larger, and I have to subtract some stuff. So this piece, this branch is going to take some work because it is CPCTC plus subtraction. There has to be some subtracting. So from my triangles, I'm stealing angle 7 congruent to angle 8. Write it over here. CPCTC, great, done. Then I'm stealing EF congruent, DH, I can't read my own handwriting, congruent to FG. Yay, 2/3 of mine is done. We can just now say angle 3 is congruent to angle 4 by subtraction, and he would lose some points, but it would be better than nothing. But let's make that happen. To get angle 3 congruent to angle 4, I do need to take the fact that angle EDH is congruent to angle EFG. That also is CPCTC. Now I told you that we're going to have to be doing subtraction. If we're doing subtraction, we need an equal sign. When we convert, our reason is congruent angles are angles with equal measure. Okay, so now I have that the larger angles are the same, and I have to subtract angles, I can't read the numbers, 5 and 6. But before I can subtract 5 and 6, I haven't said anywhere that 5 and 6 are the same. Why are 5 and 6 are the same? 5 and 6 are the same. That comes from my isosceles triangle. This given way over here. This guy needs to come around here, and it is what leads me to angle 5 is congruent to angle 6. My reason is if two sides of a triangle are congruent, then the angles opposite them are congruent. Great. But again, we're going to be doing some subtraction, so I'm going to convert that to measure of angle 5 equals measure of angle 6. I wrote the reason once, so I don't want to write it again, so I'm just going to write reason 1. Alright, subtraction goes with sum of the parts. So I need to get some sum of the parts into this group. Well, EDH is my large angle. I need to identify what that means. Angle EDH is equal to angle 5 plus angle 3. And angle EFG is equal to angle 4 plus angle 6. When I break it up into the smaller angles, that is the sum of the measures of the parts is equal to the measure of the whole. Now looking at my expressions, I have EDH. Well, this is EDH equals EFG. Well, this is EFG. I do some clever substitutions using these two boxes. I get that the measure of angle 5 plus the measure of angle 3 is equal to the measure of angle 4 plus the measure of angle 6. I'm dealing with an equal sign, and I'm replacing a quantity with an equivalent quantity. So my reason is substitution. My goal was to get 3 and 4 to be the same. I need to ditch 5 and 6. Well, here's 5 and here's 6. They're the same, which means I can subtract them away from my equation. So if I take these two boxes, and I apologize because this is going to be a little bit messy. Those two boxes together, when I subtract, I'm left with measure of angle 3 equals the measure of angle 4. Sorry, I'm subtracting 5 and 6. And my reason is equals. Subtracted from equals or equals. But I don't want them equal, I want them congruent, so I'm going to switch it to angle 3 is congruent to angle 4. I've already written this reason once, so I can just reference it and write reason 1 and there, finally, after 1, 2, 3, 4, 5, 6, 7, 8 steps, is my angle. So I have angle, side, angle, because proof is kind of jumping all over the page. But now I have my triangles. I have to look at the top to see how they were named. Triangle, DJH is congruent to FKG. And I use ASA congruent to ASA. Now there are other methods that kind of look nothing like this. That's totally fine. And I told you that I have a tendency to take the longest way. So there's no guarantee that this is the fastest method either. But this is a method that works, and I also kind of wanted you to see a refresher of subtraction and also bringing in the isosceles triangle theorems. So it is a nice method.